So hello everyone, I'm Zihao Wang from Indiana University. Today I will introduce our work, Toasting in the Dark, practical bit flipping on gray box deep neural networks for runtime Trojan injection. And in the past decade, machine learning has made significant progress, and the industry has widely adopted large-scale machine learning platforms. Companies like Amazon, Google, and Microsoft now offer machine learning as a service to meet the growing demand. And a key trend in this space is the use of pre-trained backbone models, which are either applied directly to many tasks or maybe share for others to build upon. And techniques like transfer learning, LoRa, and NetTailor enable efficient fine-tuning, further accelerating the development and performance of machine learning solutions. And more importantly, due to their exceptional performance, machine learning models are increasingly being integrated into critical decision-making systems, including medical diagnostics, access control, and malware detection. And as a result, maintaining the security of machine learning in these systems has become very crucial and increasingly important. However, as machine learning continues to achieve astonishing successes, its failures also become equally surprising. And two well-known vulnerabilities are adversary examples and Trojan attacks, where adversary examples are typically trying to find a small input perturbation that can make the input image cross the classification boundary. And Trojan attacks, on the other hand, involve data poisoning to subtly alter the classification boundary, and by embedding a trigger like a yellow patch into the training images and labeling them as a target class, the machine learning model learns to misclassify any image with the trigger as a specific target class, and maybe such as a spelling missile. And this manipulation changes the model's behavior in a subtle yet dangerous way. And in 2014, the Rowhammer attack emerged, and revealing that attackers could flip bits in memory to carry out malicious activities. And the attack works by rapidly accessing specific rows of memory and cause electrical interference that lead to bit flips in adjacent rows. And this technique has introduced a new threat to machine learning. Recent studies have shown that Rowhammer can be used to modify neural network parameters. And although neural networks typically contain millions of parameters, and previous work has demonstrated that flipping just a few bits can degrade the model's inference accuracy to the level of random guessing. And despite its potential, this emerging threat is still underexplored, and its full security implications remain clear. For example, it's not yet fully understood whether Rowhammer can be used to inject stealthy functionalities like hidden Trojans. And if feasible, such an attack could be much harder to detect, and exposing a new attack surface to adversaries without requiring access to the model's training stage, but only the runtime stage. And so in this work, we aim to answer the following questions. So are deep neural networks vulnerable to Trojan attacks at runtime? And to begin with, let's briefly review the scope of our attack. So our attack focuses on quantized deep neural networks, which are generally considered to be more robust to bit flip attacks. And since model quantization is widely used for improving computational efficiency, it's crucial to investigate the robustness of quantized models against hardware faults. And our work examines a gray box scenario where only the backbone model is considered white box, while the additional user-owned components are considered as black box. And we assume that the attacker has black box access to the end-to-end model through a query interface, and this interface only returns hard labels without any prediction confidences. And this threat model is more realistic, since machine learning models in user-facing products typically do not expose raw confidence scores, and as a result, our attack can target any machine learning classifiers. And finally, we leverage the Rowhammer attack to inject faults into the backbone model's weights. I see. So before we delve into the attack details, let me outline the attacker's objective. We aim for the attack to be both stealthy and effective. So for stealthiness, we hope that even after the attack, where certain bits have been flipped, the model's utility or the inference accuracy should remain largely unaffected. And at the same time, the Trojan task should be injected with a high attack success rate. So if an input contains a specific trigger, then regardless of the background, the classifier should consistently classify it as a target class. However, realizing such an end-to-end attack for such an objective is highly challenging, and we identify three major challenges. The first is how to score a given bit. So without full white box access to the end-to-end model, we must first build a substitute model that closely mimics the target model's functionality, and then use the goal function on the substitute model to evaluate the value of each bit. And next, we need to identify a chain of bits that are both flippable and can be precisely flipped to achieve the goal. And additionally, given the limited number of flippable bits in real hardware, we need to minimize the number of the required bits. And this can be achieved by carefully fine-tuning the trigger pattern. And to tackle the first challenge, we propose a data-centric knowledge discovery method that allows an attacker to build a substitute model that closely mimics the target model's functionality with limited queries. And at a high level, this knowledge discovery algorithm iteratively identifies the data points that are most likely to be near the target model's decision boundary. And to achieve this, we start by making random queries to collect the outputs from the target service and use the label data to train an initial substitute model. And next, we use the uncertainty of the substitute model as an indicator to identify data points that are potentially near the target model's decision boundary. In detail, we employ data augmentation to generate a large number of candidate data points and then evaluate the model's uncertainty on each candidate using the entropy on its confidence scores. And we selected the data with the highest uncertainty for the next round of querying. And this process is repeated iteratively to fine-tune the substitute model, and it has proved to be very effective for executing a gray box attack. And to tackle the second challenge, we propose an effective bit search method to locate the most valuable weight bits. And we began by using gradients to rank the bits, with the first term contributing to the attack success rate, and the second term controlling the stealthiness. And the parameter alpha is used to balance between stealthiness and effectiveness. And after ranking, we selected the highest ranked bit that is flippable and verified through a bit flip profile built using memory templating techniques. And we also ensured that the selected bit is on a page that has not been flipped before, allowing for more precise flips later on. And if the selected bit causes a significant accuracy decline, we will just remove it and move to the next iteration. And if the desired attack success rate is not achieved, the algorithm will also continue with an additional iteration. And in the end, the algorithm generates a chain of bits that, when flipped, can lead to a successful attack. And to address the third challenge, we propose an alternative optimization method that fine-tunes both the model weights through bit flips and also the trigger pattern through input adversary attacks. So both the processes aim to push the trigger embedded images across the classification boundary. We find that this alternative optimization significantly reduces the burden of each side, and thereby minimizing the number of the required bit flips. And for trigger tuning, we have two objectives. First, when the trigger is applied to clean inputs, the model should predict it as a target class. And to further enhance the transferability, we also aim the trigger to activate some salient dimensions of the backbone model's output that are most related to the target class, and to make them to large values. And a parameter lambda is used to control the balance between the transferability and the effectiveness of the trigger. With alternative optimization, we now have a precise trigger pattern and a corresponding chain of bits to flip. The next step is to flip out the identified bits in memory using Rowhammer. So first, we perform memory messaging to relocate the victim weight pages to exploitable DRAM rows using the per CPU page size. And then we use the trespass tool to precisely flip the identified bits by controlling the contents of each row. Our experiments were conducted using the following setup. So for target model configurations, we used the cipher10 and the image at datasets with 6 model architectures. And then let's review the major results. So this table shows the dataset and the model architecture configurations, and also the number of model parameters, the accuracy before and after the attack, and the attack successor, and also the minimum number of bit flips required. And as we can see, by leveraging Rowhammer, one can successfully inject Trojans across all the settings, and with an access rate close to 90%. And the accuracy after the attack can also remain at a high level, which means the attack can be highly stealthy. To achieve such an attack, we only need to flip between 11 and 136 bits in models with millions of model parameters. So as a conclusion, in this work, we highlighted the need for alternative optimization to inject runtime Trojans by tampering solely the backbone model. And we introduced a new attack which successfully injects stealthy Trojans into deep neural networks through runtime fault injection. We also developed new techniques to tackle the unique challenges of runtime Trojan injection. And our work highlights the importance of enhancing the robustness of deep neural networks against hardware-based fault injection attacks. Yeah, that's all. Thank you.